I'm Grace O'Connell, and as part of my day job, I'm a professor of mechanical engineering at UC Berkeley. And I teach the junior level materials course where we discuss material properties for various types of materials and how those properties can impact material failure. Over the years, I've collected different climbing related examples to show in class to highlight these concepts. So I thought I would share some of the examples with the climbing community. Generally, there are a handful of ways that materials typically fail. Corrosion, which is commonly known as rust, is a very common issue with metals and can weaken the material over time. This is a particular concern for materials or metals and structures near the ocean where the salt water acts to accelerate the corrosion process. When two materials rub up against one another, one of the materials will wear away over time, leaving less material to absorb the same amount of load as in the original design. This increases the chances that the material will fracture or break into two or more parts. These two types of failure generally take years to occur. Typically, when people think about material failure, they think about a material experiencing a single overload event. For example, when you drop a plate or a glass on the floor to have it shatter in a million pieces. Here you can see examples of fracture in all types of materials, including ceramics, as seen by the concrete sidewalk and the glass bottle, metal, and laminated wood composite, as seen by the skateboard in the middle. Having a material fracture into multiple pieces can be problematic, so engineers like to use materials that will deform before they fracture. Think of this as the dent in your car. The material has experienced loads that exceeded what was expected and has permanently deformed, but the loads were not high enough to result in a fracture-like failure, which is why engineers love using metals and soft polymers for their designs. However, even metals can develop significant cracks over many loading cycles, which is known as fatigue loading, and it's very similar to how we think about fatigue loading in our tendons or muscles, with one key difference: that traditional synthetic materials are not able to repair themselves. This is an image of a crack that was noticed in 2021 during an annual inspection of a bridge on the I-40 in Memphis. There are no signs of plastic deformation because this failure occurred over time due to many loading cycles as cars and trucks passed over this section of the bridge every day. Fatigue failure occurs in all types of materials, ductile materials like metals as well as brittle materials like ceramics. Rocks are brittle materials like ceramics. I can simulate what happens during fatigue failure with this card. Because it is a polymer, it will experience plastic deformation before any signs of fracture. And you can see this plastic deformation after the first time I bend the card in half, and it doesn't return to its previous shape. Over time, a crack will appear somewhere in the middle of the card. In this card, it started at the bottom half. Sharp edges, whether it's by design or due to a crack, create areas in the material that will experience even greater stress concentrations. So as I continue to apply more loading cycles, the crack will continue to grow from that point until it traverses to the other side of the card, eventually resulting in fracture. And catastrophic failure. This phenomenon also happens with both plastic climbing holds and rocks. Here's a climbing hold from Berkeley Ironworks that I usually hand out during one of my lectures when I talk about fatigue failure, because it nicely shows the fatigue lines of how the crack was propagating and growing before catastrophic failure. In this hold, the failure initiated near the bolt and traversed outwards until there was a point when the load being applied by some random climber exceeded what the remaining material of the plastic hold could withstand, causing it to snap into multiple pieces. Some materials have a good ability to resist fracture even with a crack present, like the metal beam on the bridge that was still functioning even with a crack that nearly went through the entire beam by the time it was detected. When this happens to climbing holds, you may hear people make comments about the hold flexing, thinking that it'll break any day now. I'm going to stop the video here so I don't overwhelm with too many terms. But in another video, I'll talk about a material property that helps us understand why some materials are so good at resisting cracks before catastrophic failure. For example, the steel beam on the bridge that had a crack that almost went all the way through, and the climbing hold that also had a crack that went almost all the way through before catastrophic failure. versus more brittle-like materials like glass that are less resistant to cracks.